This video lesson is about half-life, and since we were just talking about nuclear radiation and radioactive isotopes, we know that these unstable nuclei are going to be emitting particles or emitting radiation, such as alpha, beta, or gamma. And half-life is a way of talking about how long it takes for a nucleus to do that. Some will take years and years and years to go through the process of decaying. Some will take just a matter of seconds or fractions of seconds. Some will be somewhere in between minutes, hours, days, whatever. So a half-life is defined as the amount of time it takes for 1/2 of a sample of a particular radioactive isotope to decay. So the way that this would work is, let's say I have some radioactive isotope and its half-life is 5 minutes. If I have 100 atoms of this radioisotope, then after 5 minutes have passed, so after the half-life length of time has passed, then 50 of the radioactive isotopes would have gone through the decay process, and there would be 50 left over still undecayed. After another 5 minutes has passed, another half of what was there, so another half of the 50 would go through that same decay process. So after another 5 minutes, or a total of 10 minutes, we'd be left with 25 nuclei remaining, and so forth and so on. The larger the half-life, or the longer the half-life, the slower the radioactive emissions will be released. And so right here I say that it's less dangerous if that's the case. And again, it depends on perspective. So if I have a radioactive isotope that has a very long half-life, although it's only letting out a little bit of radiation over a long period of time, one of the problems with something with a long half-life is that it is persisting for a long time. Something with a short half-life, again, if we're exposed to it, we are at more risk for, again, a higher level of dosage in a shorter amount of time. And so that's why I say that the shorter half-life substances might be more dangerous. But again, there are still some issues with the longer half-life as well because of the lingering. Okay, so here's some examples of half-lives of radioactive isotopes, and you can see that they range from carbon, which is a very long time, so that's 5,715 years, to what else we've got? Radon, which is only 3.82 days. And then again, you can see what types of radiation are emitted typically from these isotopes, and you can also see then what would be formed, and we can figure that out from doing the equation balancing like we did in previous days. Okay, so what half-life tells us is, well, a lot of different information. We can use it to work backwards to figure out how old a sample is. We can use it to figure out how much of a sample was originally present. So if we look at this question, a radioactive isotope of iodine has a half-life of 8.02 days. Calculate the mass of iodine 131 that will remain after 24.06 days. Starting mass is 1.0. So let's say that we set up a little chart here. So I've got time, and we've got mass, and so let's say at time equals 0, we've got 1.00 milligrams. And so what this is saying is that after 24.06 days have passed, we want to look at how much of the iodine 131 is going to be left undecayed. So every time 8.02 days have passed, we are going to have half of what was there having undergone the decay process. So if I am at 8.02 days, what that means is that I'm going to have half this amount that was at time equals 0, and so that would leave me with 0.50 milligrams after 8.02 days. Okay, so this would be one half-life that's passed. So after another 8.02 days, so after 2 half-lives have passed, well that, again, we're thinking about a timeline here. We start at 0, 8.02 days. If I add on another 8.02 days, that would be 16.04 days. And so this mass that was here after the first half-life had passed, that's what's getting cut in half. So notice we're not going back to the original 1 milligram, we're going to the 0.50 milligrams, dividing it by 2. So that leaves us with 0.25 milligrams. Still not at the length of time that they asked us about. We were asked about 24.06 days, so we're going to keep going. So 3 half-lives, I'm adding on another 8.02 days, and so that would take us to the 24.06 days mentioned. And so, again, dividing the mass at the end of the last half-life, so that's this guy right here, And so that leaves me with 0.125 milligrams after 24.06 days have passed. So notice this is an exponential change. If we were to plot a graph of this, which we'll see on a future slide, it's not going to be linear, and let's take a look at that. Okay, so again, we can see the numbers that we just wrote down. So 1 milligram at 0 days, and then we have a half milligram of the iodine left after 8.02 days. This right here is showing the product nucleus that's left over after the decay has occurred. And so with the atomic number increasing to 54, this must have been beta decay that's going on. Regardless, we can see, again, the depiction graphically of the masses and what they look like after each half-life has been passed. And if I were to plot this, again, I can see that if I did a line graph, I can see that it's not a linear line, or a linear curve. So notice that 1/8 of the original mass is what's left over. So we've got this convenient equation to use, so you can do it out timeline fashion like I just did to calculate the mass left over, determine the number of half-lives passed. We can use this equation. So we've got the mass left over is equal to the original mass divided by 2 to the x. Okay. So, and x is the number of half-lives that have passed. So in the original problem, if we had taken the 24.06 days, that's the amount of time that they asked us about, divided by the 8.02 days, which is the length of the half-life, we would see that that gives us tells us that 3 half-lives would have passed. And so that's how I can figure out that x value. And so if my original mass was 1 milligram divided by 2 to the third, then that's where I get the 1 divided by, 2 cubed is 8, and so that's where I would have gotten the 1/16 or the 0.125 milligrams that we came up with via the timeline method. So it's just another way of looking at the same thing. Carbon is another very important radioactive isotope, the carbon-14 isotope, and because living things all are made of carbon atoms, we can use that to help detect how old something is, because basically the carbon-14 stops being replaced as soon as the living thing dies. And so if we take a look at how much carbon-14 percentage-wise is normally in a sample of carbon atoms, and then compare that to the amount of carbon-14 that's currently present, we can figure out how old the sample is. So let's take a look at an example of that. Okay, so half-life of carbon we saw already is 5,715 years, and again, that's a very long half-life in comparison to what we just saw with the iodine. So again, after another 5,715 years have passed, we're going to have half of what was there remaining, and so forth. So if I have an ancient artifact, we know that the ratio of carbon-14 to carbon-12 is 1/16, so that would be 1/16 the ratio of carbon-14 to carbon-12 found in a similar object today. And so what that means is, if I want to think about, let's say starting with a 1 gram sample, there would only be 0.0625 grams remaining. And so we want to know, well, how old is this artifact? So what we can do here is we can take the equation that we just wrote down, and we know that the numbers we have are the 0.625 grams, so that's the mass, or sorry, 0.0625 grams, that's the mass remaining. So that would go on to the left of the equal sign in the equation that we wrote. The original mass is 1 gram, right? So that would go on the top there. And then 2 to the x would be on the bottom. So basically, once we figure out what x is, once we figure out how many half-lives there are that have passed, then since we know each half-life is 5,715 years, we can work backwards. So if I rearrange this equation, so I'm multiplying 2x on both sides to get it out of the denominator, and that goes there, that's there, and then I divide both sides by 0.0625 grams divided by 0.0625 grams, so that cancels out there. So let me get rid of some of this work. So what I have now is 1 gram divided by, so 2x, again, this is after I rearranged, 2x equals 1 gram divided by 0.0625. And if I take my calculator and figure out what that is, that should be 16. Right? So 1 divided by 0.0625 gives me 16. So that means 2 to the x equals 16. So I need to figure out, well, how many times do I have to multiply 2 by itself to get 16? And the answer is that x would be 4. Let's erase that. That would be 4. So 2 times 2 times 2 times 2 would give me 16. So that means that we've gone through 16 half-lives. And if we've gone through 16 half-lives, then 16 times 5,715 gives me 22,860. 22,860, and that's years. So that's the length of time that must have passed, and therefore that's the age of the sample approximately. And there's the work done out nice and neatly for you.